Lesson 3, Ranking Functions. Part 1, Row Number. The row number function computes a sequential row number starting with 1 within the respective window partition, based on the specified window ordering. This calculation probably seems like a trivial thing, but there are a few important things to note here. Because this query doesn't have a presentation order by clause, presentation ordering is not guaranteed. Therefore, you should consider presentation ordering here as arbitrary. In practice, SQL Server optimizes the query with the knowledge that absent a presentation order by clause, it can return the rows in any order. If you need to guarantee presentation ordering, make sure you add a presentation order by clause. If you want presentation ordering to be based on the calculated row number, you can specify the alias you assigned to the calculation in the presentation order by clause. Of course, if you like, you can have presentation ordering that is different than the window ordering. You can use the count window aggregate to produce a calculation that is logically equivalent to the row number function. Let WPO be the window partitioning and ordering specification used by a row number function. Then row number over WPO is equivalent to count over WPO rows unbounded proceeding. As mentioned, it could be a good exercise to try and come up with alternatives to the use of window functions. The alternatives will tend to be more complicated and less efficient. Part 2, Determinism. When the window ordering is unique, the row number calculation is deterministic. This means that the query has only one correct result, hence, if you run it again without changing the input, you're guaranteed to get repeatable results. But if the window ordering isn't unique, the calculation is non-deterministic. The row number function generates unique row numbers within the partition, even for rows with the same values in the window ordering attributes. Because the order date attribute isn't unique, the ordering among rows with the same order date value should be considered arbitrary. Technically, There's more than one correct result for this query. If you need to guarantee repeatable results, you need to make the query deterministic. This can be achieved by adding a tiebreaker to the window ordering specification, making it unique within the partition. The following query achieves unique window ordering by adding ordered disk to the list. With window functions, calculating row numbers in a deterministic way is a simple thing. Trying to achieve the equivalent without window functions is trickier but doable. Back to the row number function. You saw that it can be used to create non-deterministic calculations when using non-unique ordering. So non-determinism is allowed. But what's strange is that it's not allowed entirely. What I mean by this is that the order by clause is mandatory. But what if you just want to produce unique row numbers within the partition, in no particular order? The order by clause is mandatory in ranking functions, and SQL Server will produce an error. You can try to be smart and specify a constant in the order by list. But then SQL Server will complain and generate the following error. So there's no direct way to get row numbers without ordering, but apparently SQL Server seems to be happy when given a subquery returning a constant as a window ordering element. Part 3, Over clause and sequences. A sequence is an object in the database used to auto-generate numbers, often to be used as keys. You use the next value for function to obtain new values from the sequence. You can invoke this function as part of a query that returns multiple rows. SQL Server 2012 extends the capabilities of the next value for function, thereby allowing you to provide ordering specification in an over clause similar to the one used by window functions. This way, you can provide a guarantee that the sequence values reflect the desired ordering. Part 4, Tile. The tile function allows you to arrange the rows within the window partition in roughly equally sized tiles, based on the input number of tiles and specified window ordering. In case you're thinking that tiling is similar to paging, let me warn you not to confuse the two. With paging, the page size is a constant and the number of pages is dynamic. It's a result of the count of rows in the query result set divided by the page size. With tiling, the number of tiles is a constant, and the tile size is dynamic. It's a result of the count of rows divided by the requested number of tiles. It's obvious what the uses for paging are. Tiling is usually used for analytical purposes, ones that involve the need to distribute data to a predetermined, equally sized number of buckets based on some measure ordering. Suppose that you want to arrange the rows from the order values view in 10 equally sized tiles based on val ordering. There are 830 rows in the view, hence, with 10 requested tiles, the tile size is 83, that's 830 divided by 10. So the first 83 rows, the first 10th, based on val ordering will be assigned with tile number 1. The next 83 with tile number 2. And so on. Suppose that you wanted to arrange the rows from the order values view in 100 tiles. When you divide 830 by 100, you get a quotient of 8 and a remainder of 30. This means that the base tile cardinality is 8, but a subset of the tiles will get an extra row. The tile function doesn't attempt to evenly distribute the extra rows across the tiles with even spacing, rather, it adds one row to the first set of tiles until the remainder is gone. With a remainder of 30, the cardinality of the first 30 tiles will be 1 greater than the base tile cardinality. So the first 30 tiles will have 9 rows and the last 70 tiles will have 8 rows. Continuing our custom, try to come up with an alternative to the tile function without using window functions. The calculation is pretty much self-explanatory. For the given inputs, this code returns 5 as the tile number. Next, apply this calculation to the rows from the order values view. Use the count aggregate to get the result set's cardinality instead of the @CNT input, and use the logic presented earlier to calculate row numbers without window functions instead of the @random input. As usual, don't do this at home. This exercise is a teaching aid. The performance of this technique in SQL Server is horrible compared with that of the tile function. Part 5. Rank and dense rank. The rank and dense rank functions are calculations similar to the row number function, only unlike the row number function they don't have to produce unique values within the window partition. When the window ordering direction is ascending, rank calculates one more than the number of rows with an ordering value less than the current one in the partition. Dense rank calculates one more than the number of distinct ordering values that are less than the current one in the partition. When the window ordering direction is descending, rank calculates one more than the number of rows with an ordering value greater than the current one in the partition. Dense rank calculates one more than the number of distinct ordering values greater than the current one in the partition. The alternative to the rank and dense rank functions that doesn't use window functions is pretty straightforward. Part 6. Rank distribution functions. Window distribution functions provide information about the distribution of data and are used mostly for statistical analysis. SQL Server 2012 introduces support for two kinds of window distribution functions, rank distribution and inverse distribution. There are two rank distribution functions, %rank and cumdist. And there are two inverse distribution functions, %cont and %disc. According to standard SQL, Distribution functions compute the relative rank of a row in the window partition, expressed as a ratio between 0 and 1, what most of us think of as a percentage. The two variants, percent rank and cumTest, perform the computation slightly differently. Let RK be the rank of the row using the same window specification as the distribution function's window specification. Let near be the count of rows in the window partition. Let NP be the number of rows that precede or are peers of the current one, the same as the minimum RK that is greater than the current RK-1, or near if the current RK is the maximum. Then percent rank is calculated as follows, and cumDist is calculated as follows. The query computes both the percentile rank and cumulative distribution of student test scores, partitioned by tested and ordered by score. Loosely speaking, try to think of the percentile rank in our example as indicating the percent of students who have a lower test score than the current score, and think of cumulative distribution as indicating the percentage of students who have a lower score or the same test score as the current score. The output of this query was formatted for clarity. Calculating the percentile rank prior to SQL Server 2012 is pretty straightforward because RK can be computed with the rank window function and near can be calculated with the count window aggregate function. Both are available starting with SQL Server 2005. Computing cumulative distribution is a bit trickier because the computation for the current row requires the RK value associated with a different row. The computation is supposed to return the minimum RK that is greater than the current RK, or near if the current RK is the maximum one. You can use a correlated subquery to achieve this task. As another example, the following query computes the percentile rank and cumulative distribution of employee order counts. The output of this query was formatted for clarity. Part 7, Inverse Distribution Functions. Inverse distribution functions, more commonly known as percentiles, perform a computation you can think of as the inverse of rank distribution functions. Inverse distribution functions accept a percentage as input and return the value from the group, or an interpolated value, that this percentage represents. Loosely speaking, given a percentage p as input and ordering in the group based on ordcall, the returned percentile is the ordcall value with respect to which p% of the ordcall values are less than it. Perhaps the most known percentile is 0.5, the 50th percentile, more commonly known as the median. As an example, given a group of values 2, 3, 7, 17, 59, 43,112,609, the percentile 0.5 is 7. There are two variants of inverse distribution functions, percentile disk and percentile cont. The percentile disk function, disk for discrete distribution model, returns the first value in the group whose cumulative distribution, see the cumdist function discussed earlier, is greater than or equal to the input, assuming you treat the group as a window partition with the same ordering as that defined within the group. Here's an example computing the median test scores using both inverse distribution functions as window functions. Here's another example computing the 10th percentile, 0.1. Do you want to learn new skills in the fastest and most effective way? Visit learnwithvideotutorials.com.